Hi, my name is Michael Pendazis, and this is online lesson number 5. Um, last lesson we talked about 3.5, the cross product, and this lesson we will talk about 4.1, real vector spaces, 4.2, subspaces, and if we have time, 4.3, linear independence. So we'll probably stop somewhere in 4.2. Okay, so let's get started. Okay, so we are starting chapter 4 right now. And so in chapter 4, our first topic is real vector spaces. And so let's start with a definition of what a vector space is. Okay? So let capital V be an arbitrary, non-empty set of objects on which two operations are defined. Addition and multiplication by numbers called scalars. Okay, by addition, we mean a rule assigning to each pair of vectors of objects u and v in capital V, instead of capital V, an object u plus v. Called the sum of u and v. By scalar multiplication, we mean a rule for associating with each scalar k and each object u in capital V and object ku. Called the scalar multiple of u by k. Okay, so this is the beginning of the definition. Let V be an arbitrary non-empty set of objects on which two operations are defined, addition and multiplication by numbers called scalars. By addition, we mean a rule assigned to each pair of objects u and v in capital V, an object u plus v, called the sum of u and v. By scalar multiplication, we mean a rule for associating with each scalar k and each object u in capital V, an object ku, called the scalar multiple of u by k. Okay, and so then, continuing, okay, so if the following rules are satisfied, by all objects u, v, w in capital V, and all scalars k and m, then we call capital V a vector space. And the objects in capital V vectors. Okay, so let me read through the first part of this definition again. Let capital V be an arbitrary, non-empty set of objects on which two operations are defined, addition and multiplication by numbers called scalar. So we have a set V, and we have two operations, addition and scalar multiplication. Okay, a set and two operations, addition and scalar multiplication. By addition, it's a rule that if you take two objects, u and v and capital V, we assign another vector to it, to that pair, u plus v. Okay, the sum u v. So we so we take any two objects, u and v and capital V, and we assign to that pair of objects in capital V another object, u plus v. Okay, which is also an income. And then, if by scalar multiplication we take a scalar k, a number called a scalar k, and a vector u, and we assign to that pair another vector k times u. Okay? And so the following rules I'm about to list, if the following rules are satisfied by all objects u, v, w in set capital V and all scalars k and m, then we call V a vector space and the objects in V vectors. Okay, so I'm going to list 10 rules on the next board. And so if all 10 of those rules hold for any arbitrary choice of three objects, u, v, and w in the set capital V, and for any scalars or constants k and m in capital V, if all 10 of those axioms or rules hold, then the set V, the operation of addition and the operation of scalar multiplication, those three as a team, all three of them is called a vector space. Okay, so I'm going to write 10 rules or laws on the board now, and those 10 are going to have to be satisfied. Okay, so I'm going to have to erase this. You can pause the video before and you can look at this or go back to this after you look at the 10 rules I'm about to write on the next board. Okay, so the 10 rules are: 1, if u and v are in the set capital V, then u plus v is also in the set capital V. Okay, this is called closure. This is called the closure rule, that if you take two objects in V and you add them, you also get another object still in V. U plus v is still in V. The second rule is that u plus v equals v plus u. So the second rule says that the addition of vectors is commutative, meaning the order of the addition doesn't, you can switch the order of the addition. U plus v equals v plus u. That's called commutativity of addition. 3, u plus v plus w is equal to u plus v plus w. And so this is called associativity of addition of vectors. And so this is u plus v plus w equals u plus v plus w. The parentheses mean you add these two first and then this, and this parentheses mean you add those two first and then that. 4, there's an object we call 0 in capital V, called the 0 vector of V. Such that 0 plus u equals u plus 0 equals u. Okay, and this, so all these rules hold for any vectors u, v, w. So in 4, we're thinking about any vector u in any object u in the set capital V. And so we're saying in 4 there's an object we call 0, which is the 0 vector of V, such that if you add 0 to any vector u, any object u, you get u. So 0 plus u equals u plus 0 equals u. That's 4. 5. For each in capital V, there's an object little v. There's an object negative u in capital V, such that u plus negative u is equal to negative u plus u is equal to 0. Okay, so for each vector u, for each object u in set capital V, there's an object negative u in capital V such that u plus negative u equals negative u plus u equals 0. Good. And 6, if k is any scalar, and u is any object, and u is any object in capital V, which we already know, then ku is also in V. Okay, so rule 6 is that if k is any scalar and u is any object in V, then ku is also in V. 7, k times u plus v is equal to ku plus kv. 8, k plus m times u is equal to ku plus mu. 9, k times mu is equal to km times u. And 10, 1u is equal to u. Okay? 10 seems obvious, but this could actually be false. So these are the 10 axioms which have to hold for a set V and an operation of addition and scalar multiplication, those three things, to be considered a vector space. Okay? So the easiest way to, not the easiest, but I think the best way to start is just to see all 10 of these axioms. And so there are 10, these are the 10, okay? So you have to study, in order to understand this completely, you have to study this list, you have to think about it for a very long time, and spend some time on this, right? So one is closure of addition. If you add two objects in V, you get another object in V. 6 is closure under scalar multiplication. So if you take a scalar k and an object in V and you multiply them, scalar multiply them, you get something else in V. So 1 and 6 are closure, is called closure. Okay. Also, 1 through 5 is about addition, and 6 through 10 have to do with scalar multiplication. So if you wanted to break this up into two parts, part 1, 1 through 5, would be about addition, and 6 through 10 would be about scalar multiplication. So here, addition is 1 through 5, and it's not multiplication, because you call it scalar multiplication. So even putting an x here for times, it's scalar multiplication. Okay? So 1 through 5 talks about addition, and 6 through 10 talks about scalar multiplication. Right? All 10 axioms have to hold. So 1 and 6 are closure. This is called commutativity. This is called associativity. This is called the identity axiom, and this is called the inverse axiom. Okay? These kind of axioms appear a lot in algebra. And so if you're familiar with algebra, or if you spend time with algebra or this, when you go between one subject to the other, this is kind of easy to know if you know all these properties already from other places, okay? Okay, so talking about 4, because this maybe is new. 4 is saying that there's an object in V where if you add it to any other vector, you get the same vector back. So if you start with any vector u and you add this, if you start with any object u and you add this object called 0 to it, you still get u. And so that's the property of this, what's called the 0 vector. Okay? The 0 vector doesn't have to actually be 0. You can have weird vector spaces where your 0 vector is not 0 at all, the normal looking 0. But if it behaves in this way, we call it the 0 vector. And so the 0 vector is not a vector that is 0, the number 0. It's an object that has that the property that when you add it to anything, you get that same thing again. Okay, that's what a 0 is here. Okay, and 5 is called the inverse property because if you take any object u, it has an inverse under addition, meaning there's some other object in the set you can add to it to get 0. That's the inverse property. Okay? If you take any object little u, there's some other object, we call it negative u, where if you add it to it, you get 0. That's the inverse property, okay? And negative u doesn't have to be a normal, just multiplied by -1. It's just another object that you can add to it to get 0, okay? So if you take an object u, and it's a weird object, right? And you find that some other object you could add to it to get whatever the zero object is, that negative u does not have to be -1 times. Well, the normal, you'll see what. Okay, and then